Hello and welcome back to the Raspberry Pi coding channel. This is Humans vs AI, video 9, and this is the first video where we introduce machine learning into our game. Quick reminder, a Patreon account. I think you know this by now. If you'd like to see the code, or have access to the code, shall I say, and early access to the videos, please do visit my Patreon account if you'd like. Thank you. Moving on then, I've got a few slides before we get to the code. Very important slides in my view. The first thing, I like to play this one because it's quite satisfying to watch. In the very first video that I did in this series, I showed this animation as a sneaky peek into what we're going to try to achieve. We have already achieved the game mechanism that allows us to move this green dot around and collect energy, which actually was done relatively quickly. It might not seem it from going through all of the videos, but it was done very quickly as far as games go by making use of Python Arcade. The thing that we don't have is the intelligence to do what's being done on the screen, which is to go around and collect the energy efficiently and quickly. What we do have is an ability for a player to use the W, A, S and D key to move around and collect the energy, but not compete against an AI, or for the AI just to play the game like it's doing here. So we're going to look at creating that. Now to do it is to learn the basics of reinforcement learning. And in order to make sure that we are expecting the machine to perform in a reasonable way, we need to understand what the reward landscape that we're going to construct actually looks like. Bearing in mind that everything is in code, it's very hard to mentally visualize the reward landscape that we're constructing. So one of the things we're going to do is we're going to, not today, but in a later video, we're going to create this. This is a rendering of the reward landscape. And as we go through the videos, we'll talk more about what the reward is and how we create it. But what this reward landscape is showing is a colorized contour, essentially, of reward, where red is high reward and blue is lower reward. The play is the green dot at the bottom, and the yellow dots are energy. You'll notice that when you've got clusters of energy, there's a lot more red. This is by design, and that's constructed by the reward shaping that I've done for this game. Without this visualization, it's very hard to know if it makes sense. So it's really important to be able to visualize your reward landscape, which is why we're going to do that in this video series, to show you what it looks like and why it matters. So we'll be doing that. I will say this is not what the machine learning model sees. What it sees is a big flat list of numbers, the input state vector. But this is what we want it to learn. This is the relationships we're trying to get it to learn, because this is what we're rewarding it on. So i.e., you're going to get a high reward if you go towards the energy. Okay, and the last video is a sneaky peek of the game playing itself. So let's have a quick look. This is what we're going to achieve by the end of the next few videos, when we've got intelligence built in. So none of these are human players. This is the game playing itself. Now, an interesting fun fact here is that each of these players is the same model. It's the same trained model. It is behaving independently, though, because of the fact that each one starts in a unique position. And so their state, their input state into the model is unique. The input state is going to be, and we'll see this today, is going to be the relative position of the player compared to the energy points. So it matters where the player is as to what decision it's going to make, which is why, despite these all being the same model, the exact same intelligence, in a sense, they all do independent things because of their starting position. And I like this video because they all converge on, it's not actually the last data point, but the last but one energy point, not data point, energy point. They all converge on that in a big race at the end. And in the end, player 3 wins. The winning condition, by the way, for this particular setup was to collect 5 energy points of the 16 that were available. And you can see the red player has a bit of an advantage at the start. It's near to this, as is the yellow's near to this and the blue's near to this. But once red has collected this one, it's then got 1, 2, 3, 4 more that are reasonably close. And if you look at the other ones, they don't really quite have 5 within quick, convenient range, which is why red has won. Effectively, the player that starts nearest to a clump is likely to win with this game. But of course, this game is overly simplified. It's the starting point for what can be much more complex and interesting. We have to start somewhere. So this is where we're going to get in the next few videos before we start making it more interesting and complex. So let's go over now to the IDE and let's get started. Okay, without laboring material that we've been through in previous videos, I just want to remind you that the game is now split across multiple files. It was in the last video that we split them out across multiple files. And we've got a number of classes. The main class for the game is called Game App, and that's inheriting Arcade Window, which is what allows us to get the game loop. And if you recall, the game loop allows us to tap into 2 methods, onDraw and onUpdate, both of which run with every frame of the game. And it's here where we can put in the logic in onUpdate for the game state, and in onDraw is where we put the rendering. Okay, hopefully they're really important, so I thought I'd just remind you about that. Player is an object when it's created from the class, player class. So here's the player class, and we create for each player a player object, and they have state. For example, they have a target X and target Y, which is the position we want the player to be at. This is how we achieve movement. And we have a current X and current Y, which is where the player currently is at. That's where it's being rendered. So I'm going to play the game from the previous video very quickly as a reminder. So in the current state, none of the players apart from player 1 are playable, because the only input into the game at the moment is the keyboard, and we only allow the keyboard to change player 1's position with the W, A, S and D keys. So I can move this player around, and it's doing that by updating the target X and target Y variables for the player class, which leads to the animation, because the rendering loop is trying to get the current X and current Y position to match the target X and target Y position, so it'll animate to achieve that, and then it snaps to grid. And if I collect an energy point by going over the top, in this case we get game over, because the game is set up such that collecting 1 energy point will lead to the game over condition being true. Right, I won't labour this anymore. We'll get on now to the machine learning. Okay, close that down, close that down. Right, so in this video then, we're going to just be working in main.py. Nothing else is going to change in any other file. And we're going to create 3 new methods inside the game app class. So the game app class is here. So I'm going to scroll down and we're going to create 3 new methods. The first one is going to be getting the game state out of the game environment. So let's quickly run through this method here. It's not big, it's relatively straightforward. Now, if you've been watching this series to date, I doubt you're a Python newbie. But if you are, these are called lambda functions, and I've got 2 of them. And what they do, they are functions, they're not individual, well, they are an individual line, but it is a function in that it takes an input and produces an output. You can see that because it's called a lambda here. And what it does, it says normalize x takes an argument of x, and what it gives you back is x divided by, in this case, grid size x, where grid size x is from the constants file, and grid size x is the size of the grid in the x dimension. So these are literally doing what they say, they are normalizing. And the reason we normalize, this is a good pausing point, is that the input into a machine learning model, and that's the whole reason of getting the game state, is so it can become an input into the model, they have to be normalized. Depending on the activation function, they're usually normalized between -1 and 1 or 0 and 1. In this case, we're normalizing between 0 and 1. Now, the 2 things that we really need from machine to learn to collect energy are the position of the player and the position of the energy. Strictly speaking, it needs to know the difference between the 2 in order to move towards it, if we think about it. So there are lots of ways we can approach this problem, and when we get down to the flatten game state method, we'll be talking about those approaches. But for now, we just need to get the game state out of the game. That's what this method is doing. So after these two normalized lambda functions, we're getting the player state from the player's current x position. So getGameState takes player object as an argument, and we're extracting the current x and current y positions from it here, and we're normalizing them. And we're putting them into this dictionary with the key called position. So position, the key now has an x and y value as a tuple. So that's what player state is, it's extracting that. Then energy positions is the same really. It's just normalizing the energy positions, energy 1 and energy 2, coming out of this array, energy points. If you remember, energy points is a state variable, which is a variable belonging to the class, the game app class, which contains a list of energy points that are currently active in the game. So that's giving us the energy positions list. And then the state, therefore, is simply a dictionary of players containing player states and energy positions containing energy position states. Now, the player's state will only ever contain one player because it takes player as an argument. It depends what player it is. It is conceivable to include all players in this state so that a given player knows about the positions of other players. But we're not going to concern ourselves with that at the moment. We're not going to let each player know about its competitors at the moment. We're going to have them just focus on the problem of gathering energy, which is why player state is just the state of the current player, x and y position. So the state dictionary created here is returned from this method. That's what GameState returns. Let's move on to flatten GameState then. So I've mentioned that we have to normalize the input to the machine learning model, the state vector or the observation in terms of reinforcement learning. Same thing, has to be a one-dimensional vector, a big long list of numbers. So we've said that, and as we go through flatten GameState, we'll pick up another few bits and pieces that are very important for machine learning. Okay, so flatten GameState, the first thing it's going to do is it's going to get the player data out of the dictionary. Now this does seem a little bit fruitless because we've just put it into a dictionary, but there's a good reason we've separated out these two concerns between these two things, because this can grow to have more players, and we can add more game state up here. So in case any of those eagle-eyed viewers were noticing that this was kind of reversing what we've just done in a way, yes it is, but for good reason that we've separated these two things out. Okay, so anyway, back to the point. Player data, we're extracting from the dictionary, from state that we've just created. So flatten game state takes state as an input, so it's an argument, and that's what was created here. And it's extracting it in what's called, well, this is called list comprehension. Again, if you're new to Python, look it up. All it's doing is it's looping through each element of state players. So it's looking at the dictionary players, looping through each element. Now, of course, currently there's only one player, so there's only going to be one element. P is going to be that one player that we populated in our player state. And it's getting the x and y coordinates and putting them into a list within this list. So it's a list within a list. So that's x and y coordinates for the player. That's what player data is. Okay, now here's the bit that the machine really needs in its data set. Relative positions. So we're going to give it not the position of the energy, but rather the relative position of the energy compared to the player. So the difference in x and difference in y. We could just feed the model the position of the energy, and it does work, but it seems unnecessary to expect the model to understand that it needs to move towards these positions. It's easier, you're saving a little bit of complexity by offering it the relative position. So that's what we're doing here. So we're taking the position of the player in x and subtracting the position of the energy in x, and then doing the same in y to basically result in a list of relative positions between the player and the energy. And again, this is using list comprehension, where it's going through every item of the dictionary key energy positions, extracting it as E, and then going through and producing an output into this list. So list comprehension. Okay, so that gives us player data and relative positions. Now, talking about important things to know about machine learning. So the machine, the model, will learn, if we're not careful, that the order of the input data really matters as to what reward it receives. It can learn that by accident, and it can fixate on that, even though it's not a feature. that we want it to fixate on. To stop that happening, we sort the relative positions in order of the distance between the player and the energy. So in order of the magnitude of the relative position. And we do that using the Euclidean distance calculation. So that's sorting basically in order of distance, which means the left-hand side of that list is always going to be closer to the player. That helps with the training process. It also helps avoid confusion. So that's that. And then the all-important part, which is where the function gets its name from, is we flatten. So obviously the relative position data are a series of x, y lists. What we do here in this line is we break that down into a straight long list of x, y, x, y, x, y, x, y. So it's a long linear one-dimensional list instead of multiple two-dimensional lists. Sorry, instead of multiple one-dimensional lists, it's now one big one-dimensional list. I hope that makes sense. So that's what that is. We've flattened the array out. And this is now another piece of information for you on machine learning. The input state vector, so what you feed the model, the observation of the player, essentially. In our case, the relative positions. The length of that vector has to stay the same. You can't change it. Excuse me. When a player consumes the energy, they get removed from the list. So let's just go back up again. If you recall, our state contains the energy positions array. We know that, we've just been talking about it. But it gets that from the state variable energy points. Energy points get smaller as the energy is consumed by the players. Which means, when we get down here, the input vector into the model gets smaller. That's not possible. The machine learns to give an output for a given input. That input length or shape of the vector has to be the same for it to work. So we can't change it. So what happens here then is we say, okay, so if the length of the array is less than the full length of how many energy points the game starts with, times 2 by the way, because there are x and y coordinates for every position. If that's true, then pad the end of the array out with -1 values. Because -1 is not within range of 0 to 1, which is what we're using as our normalized range. So what this means is we're making them very distinct, that these energy items have been collected, so the player will no longer learn to collect them. Now, it won't implicitly learn that -1 equals that. We have to explicitly explain that as part of the reward process, which we'll explain later. But by distinguishing, by really singling out the energy which isn't in play anymore that's been collected and giving it a number that's very different from 1 or 0, that helps it learn that they are no longer in play. Now I will say, for interest's sake, there are different ways of doing this. If we didn't want to have to pad the array out, we could do something called one-hot encoding. We could use convolutional networks with one-hot encoding, which is something I won't get into, but it might be something we show later, as it's not too hard to substitute it in as an alternative approach, but it doesn't scale as well for various reasons. So this is a good way of dealing with this problem, and it's common, padding. Okay, next on the list then is calculating the relative distance. So let's just pause a minute and say that the first feature that the model will learn on is the relative position of the energy to the player. We're going to help it out by providing it with a second feature. And that second feature is an array of relative distances, which is of course not x and y coordinates anymore, but the actual Euclidean distance, which is calculated here, between the player and the energy. This just helps the model recognize that there's a distance component. We're basically helping it. Again, we don't need to give this. If I was to take this out, it would still work. But it works a little bit better by putting it in. So once we've created that relative distance calculation of energy against player, in X and Y coordinates. It's a single value per coordinate. We then sort it, creating the relative distance sorted list. As above, we have to pad it out for the same reason. We can't have this getting smaller. And of course, it is also based on the energy. So as energy is consumed, this list is going to get shorter. So we pad it out like we did before, which is what we've got here. The only difference is we don't have energy times 2 because there aren't 2 coordinates. It's just a single point per coordinate. It's a distance. And then we use the plus, which is a concatenate operator, to concatenate the 2 lists we've just created, relative positions flat and relative distances sorted. So there are 2 features. And basically, congratulations, this is your training data set. This is what's going to go into the model for it to train, but also this is the state vector. This is the observation. This is what the model sees. It's all it sees. So with every loop, every iteration, it is going to see simply a list, a flat list of the relative position between the player and the energy. It doesn't know where the player is on the grid, by the way. It just knows where the distance is between the energy and the player. And it also knows the relative distance between them. You might be thinking, well, how does it know it's not going to run into the edge of the grid? It doesn't to start with, and it will probably run into the edge of the grid. But it won't learn that that's a good idea because it's going to go for the energy. And of course, the energy is always inside the grid. Now, as I say, it's a deliberately simple problem. Okay, so that's flatten game state. Now, you will have noticed, of course, that flatten game state takes the state as an input. Get game state provides a state as an output. These 2 methods are often going to be nested together. We get the game state and then we flatten it. So they'll often be seen together. Okay, so they're 2 very important methods to allow a machine to understand the game environment. This is giving it vision. It's what's called the observation. And this output is the observation that goes into the machine. I think I've labelled that enough. So we're going to move on to the final method for today. And that is machine learning, ML_set target position. I've prepended it with ML to make it clear that this is a very specific machine learning method. It's to set the target position of the player by the machine learning only, by the model. So if you remember, currently a player can be controlled by the W, A, S and D key. And what those keys do is they set the target position for the player. That's all it really does. Well, we need the equivalent in the machine learning world. And that's what this method does. So let's run through it. First off, it says effectively, if it's not a player, don't do anything. Just return from this method, i.e. don't set a new target position. This is unlikely to happen. It's just good practice. And then it says, if the player's in transit, also do nothing. So the point of this is, don't let the machine make a decision if it's in transit. There's no point. It can only make a decision when it's snapped to grid. Okay, makes perfect sense, really. That's the first thing. Then it converts the action into a movement. Now let's pause here because you haven't seen the output from the model yet. But I can tell you what it's going to be. So firstly, I'm going to go into the constants file. You'll recognize this from previous videos. If we scroll to the bottom, you'll see we've got a new input. It is the only change, by the way, so don't worry, nothing else has changed anywhere else. I've created an actions array, and you'll see it contains key value pairings 0, 1, 2, and 3. So just so you know, 0, 1, 2, and 3 is the expected output from the model. It's going to produce a number between 0 and 3. And we then need to convert those numbers into an action that we can actually use to move the player. So we've translated 0 into moving up, translated 1 to moving down, we've translated 2 to moving left, and we've translated 3 to moving right. And that's because right is 1 increment in the x position, left is -1 increment in the x position, moving down is 1 increment down in the y coordinate, and moving up, of course, is 1 increment up in the y coordinate, which is why it's 0, 1. Hopefully that's clear. This is a mapping exercise, essentially. So we're going to train the model to produce, just go back here, a number between 0 and 3 based on the input state. The input state being, of course, this stuff, and the output state being between 0 and 3. and we're going to reward it based on its actions. That's what's going to happen eventually, and we'll get to that if that all sounds confusing later. Point is, though, we need a method that allows us to move the player based on the output from the model. Okay, so what this method does, it says, I'm going to take in the player object, since we need to know the player's position and we need to update the player's target position. We're going to take the player object as an input, and we're going to take the action as an input. So at this point, we're not saying we've got an action in here. We're saying we're going to take the action as an input. So at some point, we've got to get the machine learning model to provide us with an action, and we'll get to that in a video or 2 videos time. But assuming we've got that action, and that action is a number between 0 and 3, we can use this line here to extract that translation. So for a given number, from the constants file, we'll get our little tuple of dx and dy, which means change in x and change in y, where d stands for delta, which is a change. So we get the tuple out of the action array, which we've got here, or dictionary in this case. Okay, this is the get method for getting that, to get that information out of actions, where the 0, 0 here is the default response if there isn't a match. That's kind of what happens if you can't find a match. So that'll give us the x and y position movement that we're looking for. The next thing here, okay, is, so the machine has made a decision, it's given us an action, and we know which way we want to move. So let's, for fun's sake, it gave us a number of 2. Then if it gives us a number of 2, then we're going to get -1, 0 back. So action is 2, okay, we get 0, 1, so we get -1, 0. So dx -1, dy is 0, okay. The next 2 lines is saying what we should do. So what is the new x and what is the new y coordinates? So new x is the player's target position now, plus the delta in x. And new y is the player's target position y, plus a delta in y. The min and the max, this whole content here, including the grid size x and grid size y, simply limits new x and new y to between 0 and the max grid size. It stops this new x being outside of the bounds of the grid. It's just a syntactically nice way of saying you can't go outside of 0 to grid size x and 0 to grid size y in the y axis. Okay, so we've got a directional movement converted into a new position in grid space. I hope that makes sense. Now, the bit here is saying, okay, but what happens if we hit the edge of the grid and then the machine gives us an action which takes us outside the grid? That's what all of this is doing. So what we do is we set a variable at wall equals to false, which says we're not at the wall by default. And then we look to see if we are at the wall. So all of these component parts of this if statement are the 4 sides of the wall. And it's saying if any of these statements are true, then at wall is going to be true. Right? So if the player is already at the wall, it's equal to true. The next question is, okay, we're at the wall, which is one of the conditions for the next statement. Have we moved? Now, this is important because if we haven't, if current x is equal to new x, let's take that as an example, that means we're at the wall and the machine has tried to go beyond the wall because it's not been able to move. And that's because, as I've just mentioned, we've limited it to the constraints of the grid. It can't go beyond the grid because of this statement, which means if it's trying to, if action results in a dx, dy that's trying to go outside, new x and new y won't change. It's going to stick where it was because of the max and min statement. So back to this then, this means this will be true. If the player is already against the wall and the action is trying to take it outside the wall, this will be true and this will be true, which means we do nothing. So it's a very, well, I'd say quite simple, probably not very simple, but quite simple way of saying you can't move beyond the wall. If the machine is trying to, do nothing. If it's not trying to go beyond the wall in one of the 4 directions, then we return the output from the set target position method, which is a method belonging to the player class. And you'll remember that from a previous video. And all that's doing, by the way, is setting player target X and player target Y. That's all it's really doing. So there you go. You now have a means by which you can take an action, 0 to 3 value, convert it into an X and Y delta, which way you want to move, convert it into a grid position, which is constrained, check if it's stuck against the wall. If it's not, you update the player's target position. And as you know from previous conversations around moving with the keyboard, that basically means the player will move. The animation will kick in to get current X and current Y to equal target X and target Y. Okay, it's a lot there, but that's basically what we've got. We've got a way in which the machine can now influence the game. If only we can get an action, of course, we need an action. We've got a way in which we can flatten our game state for a machine to understand, because it has to be a one-dimensional vector. And we have a means of getting the game state, the bits we think are important. And I've explained that what's important to do this in the simplest possible way, which is kind of my objective here, is to provide the game with, the model with the relative position of the energy to the player and the relative distance between the energy and the player. And that's down here. And that's going to be our input state. I hope that's clear. There's a lot of stuff there, but they are the foundations. So that's this video done. In the next video, we're going to progress this further to start using these methods and to start getting closer to a training loop. We've got a few videos to go before we get there, but we're well on our way. I hope you found this useful. I hope it's been an insight into reinforcement learning, at least at a very basic level. I hope you've taken note of things like the importance of sorting the input space, the input vector, padding. If you change the input state size, you can't, so we have to pad it out, normalization, and things like that. Okay, thank you very much for your time, and I hope to see you in the next video. Thank you.